we're asked to find the IUPAC name for this molecule. What you want to do is start counting at the longest chain. And normally I like going from right to left. So we can do, let's see, 1, 2, 3, 4, 5, 6, 7. 7 is a pretty big number. That's most likely going to be our parent chain, but let's see if we can find anything larger. So we already took this path, right? Okay. What else can we take? We can take 1, 2, 3, 4, 5, 6. But if I go here, this is a 6. 7 is larger than 6, so I'm going to take the 7 route. 7 carbon route. Okay, so if we're saying that this molecule is 7, then we will have a what? We will have a 1, 2, 3, a 3-methyl. A 3-methyl. The reason why I started counting at the top is because I'd rather have a 3-methyl than a 1, 2, 3, 4, 5. So 5-methyl is not as good as a 3-methyl. You always want to have the lowest number possible. In this case, 3 is going to be less than 5. So I'd rather have a 3-methyl than a 5-methyl. Okay, well, what is going to be our other substituent? What is our other group that is attached to us? Well, we have this group, and it's kind of like a Y shape. Whenever you think of Y, think iso. Okay, so think iso. What is this? Now we know it's a Y shape, so it's going to be iso-based, and we have to come to carbons. So that's 1, 2, 3 carbons. 3 means propyl, so this is the isopropyl. This can also be noted as a 1-methyl ethyl. So it's isopropyl, but the IUPAC name for isopropyl is 1-methyl ethyl, because isopropyl is more of a common name. This is the common name. Okay. And it is on what? It is on 1, 2, 3, 4. So that is a 4. 1-methyl ethyl. And if we take this together, we will say that this is what? Well, isopropyl, the I comes before M, right? We use the I in iso for alphabetical ordering. So you can say 4-isopropyl, but since it's IUPAC, we're going to be using the complicated name. We will say that this is 4-1-methyl ethyl -3-methyl heptane. The heptane comes from the 7 carbons, so this is 1, 2, 3, 4, 5, 6, and 7. So that is a 4-1-methyl ethyl 3-methyl heptane. Of course, this right here is just isopropyl. That's just a more complicated IUPAC name, right? So this is IUPAC. And this is going to be common. Of course, if you didn't know what the IUPAC name for isopropyl was, you can eliminate answer choice A, B, and C because they have hexane, and we're dealing with a heptane. Heptane is 7, hexane has 6 carbons. The reason why E is not correct is because it has a 5-methyl. A 5-methyl occurs if you do this. It occurs if you do this right here. Let's see if I could just draw it out. Right? It occurs if you number it from 1, 2, 3, 4, and 5, right? So this is saying that you numbered it from the left to the right, which is incorrect. We don't want to have a 5-methyl. You know, that's too big of a number. We actually want to have a 3-methyl. So E is incorrect because it has a 5-methyl, and we want to keep that number as low as possible. So 3 is going to be better than 5. That's why E is incorrect. A, B, and C have hexane. We're dealing with heptane. We can immediately cross them out. Now we're asked to find IUPAC name for this molecule, and if you're not good at finding the IUPAC name just from the condensed structure, you can actually write it out, right? So we can have I recommend writing it out. So we have a carbon. There are 3 hydrogens attached to it. Now this carbon has a hydrogen and another carbon. Then it's connected to another carbon right here. Okay, and this one will have hydrogens right here. It's going to be connected. Okay, so now we count the longest chain for it. So we will say 1, 2, 3, and 4, right? And if you want to do a line structure, it's going to look like this. It's going to look like this right here. 1, 2, 3, 4, and kind of like a CH2. Whatever that is. Okay. So we have 1, 2, 3, 4, so this is actually a butane. If we know that it's a butane, then it's not a pentyl, right? It's not pentane. So we can eliminate A, and we can eliminate B because I don't know what an isoamyl is. I've never heard of it. I don't think it's in this chapter. So we can eliminate B as well. And let's see. Well, butane is more than 3, right? Butane is actually 4. Answer choice E has propyl. Propyl means 3 carbons. And we're not dealing with 3, we're actually dealing with 4. So we can eliminate E. Okay. So the only thing that have butane in it is C and D. So what is the answer? Well, think about it in this way. What do you see here? We have a what? We have a 2-methyl. If you number it from here, 1, 2, 3, and 4, that is a 2-methyl. So we can say 2-methyl butane. So that is a 2-methyl butane, or actually not butane, but butyl. 2-methyl butyl, right? And so that would be answer choice D. So find the IUPAC name for this molecule. Always start with the longest carbon chain. So it's not going to be this one, right? It's not going to be that. Instead, what we will do is this. We will say that is the longest chain. If we do that, we have a chain of 9. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so 9 carbons, 9 gives you nonane. Nonane. And so we can eliminate answer choice A, B, C, D, right? So just by knowing the longest chain, we eliminate practically all the incorrect answers. A, B, C, and D all have heptane, octane, but we have nonane. So if you're in a rush, just try to find out your longest carbon chain and see if some incorrect answers can be canceled out. See if you can eliminate some wrong answer choices. But let's continue. I'd rather count left, or I'd rather count downwards going upwards. So I'll count right here. 1, 2, 3, 4, 5, 6, 7, 8, and 9. Because if I count right, this is actually going to be 1, 2, 3, 4, 5, 6, 7. I don't want this to be a 7-methyl. I want it to be a 3-methyl. I want to keep the methyl group on the lowest carbon. And so we can say that this is a 3-methyl. And this is what? Well, it looks like a Y shape, doesn't it? It kind of looks like a Y shape, right? So let's count the carbons. 1, 2, and 3. 3 carbons. Well, if it's a Y shape, then you know it's going to be iso. It's iso, and it has 3 carbons, so we'll say it's a propyl. Now, it's attached to the 4th carbon, so we will say 4, isopropyl. Isopropyl dash 3 dash methyl nonane. Nonane. Okay. Notice that the isopropyl came before the methyl group because in the iso we use the I for alphabetical ordering, and for the M it's the same thing, right? You should know that isopropyl can also be called a 1-methyl ethyl. That's also equivalent for isopropyl. But yeah, so this corresponds to answer choice E for isopropyl 3-methyl nonane. So we have to find the IUPAC name for this molecule. Well, notice that this portion is a Y shape. So you know your answer has to be iso. If you don't see the Y shape, well, it takes a lot of practice, but yeah, I can understand how you say 1, 2, 3, right? I understand how you can do that, or rather 1, 2, and 3. But you have to kind of look in a more broad sense. You have to kind of zoom out and look at the big picture. So yeah, this is a Y shape. So it's iso. Now we count the carbons. That's 1, 2, 3, and 4. So we know it's going to be isobutyl. Do you have anything attached to it? Well, yeah, we have a bromine. So we could say isobutyl bromide. Isobutyl bromide, which is answer choice A. If you didn't know that, you could look at your answer choices and realize that this is not a tert butyl. Tert butyl bromide would actually look like this. So you would have 1, 2, 3, and 4, right? You would have 4 carbons like that, but notice that it's in a T shape. And it's a T shape, so this carbon right here, this carbon would be tertiary because it's connected to 3 other carbons. So that's why it's called a tert butyl. But we don't have a T shape, we actually have a Y shape. So Y is for iso, so this cannot be it. Right here, answer choice C is just butyl bromide, but you're missing the iso part. See, a butyl bromide would actually look like this. 1, 2, 3, 4. So 1, 2, 3, 4. You can have it like right there. That's a butyl bromide, right? So we don't have that. Answer choice E is not formatted correctly. So bromosec butane. That's incorrect. It should actually be sec bromobutane. But we don't have a sec butyl. A sec butyl kind of looks like this, if I remember correctly. So 1, 2, 3, 4 is going to be attached on the second carbon. And then this one would actually, it would be attached to like this other parent chain, but we don't have that. So you're mainly dealing with like secondary carbons. The second carbon, we don't have that. And so it really factors in on the shape. Realize that this is the Y shape, and a Y shape gives you an iso prefix. A prefix is just something that comes before a word. So the prefix for isobutyl would be iso, and the root word would be butyl. So a Y shape is for iso. Right? That's the trick. For this one, it's kind of tricky because instinctively you would think that this is a Y shape and that it would be isopropyl, but that's not the case here, right? That's not the case. We're going to start numbering our longest chain. So we have 1, 2, 3, 4, 5, 6, right? So we have 6 carbons in this chain right here. That's 1, 2, 3, 4, 5, and 6. So we're dealing with a hexane. So we can eliminate answer choice A, B, and E because A and B deal with pentane. Pentane has 5 carbons. We have 6. Answer choice E has butane. Butane has 4 carbons. We have 6. So we're mainly dealing with C and D. All right, so let's start numbering. Would I number going this way? Well, not exactly. Because if I number it in green, this is the correct way. 1, 2, 3, 4, 5, and 6. I'd rather have chlorine and methane or methyl on 3, right? Because the red one shows them on 4. And you know, if I can have something on a lower number, like chlorine and methyl on a lower number, that's good. I want 3. This methyl group right here, it could be on 2. I'd rather have a 2 methyl than a 5 methyl. The bromine, I mean, it's not good that it's on 5, but you know, these 2 sections right here, if I can have them both on a lower number, that's great. I want that. So we will say that the green one is going to be the correct way to number it. So that is a 2-methyl. And that is a what? We have 2 things on the 4th carbon. On the 3rd carbon. So we have a what? We have a 3 chlorine and a 3 methyl. And then we have something on the 5th carbon, so we have a 5 bromo, and then we have a hexane. Okay, so no double bonds, no triple bonds, no alcohols. So now that you listed everything in the molecule, let's bring this all together into our boiling pot, and we're going to make some soup. We're going to make a name. Okay, so what's the first thing that I do? Well, I'm gonna sort it. I'm gonna organize this in alphabetical order first. So I'm gonna have chloro before methyl, but I'm gonna have bromo before chloro because B comes before C, right? So we have 5 bromo. We have 5 bromo, 3 chloro. But do I say 3 methyl, 2 methyl? No, I don't. If I have 2 methyls, right, then that's a dimethyl. So that's a dimethyl because that means we have 2 methyls in this molecule. But notice that we have different numbers. So I'm going to say this. I'm going to say 2, comma, 3, dimethyl. Do I have anything else? No. So we say hexane. The 2 and 3 means, well, let's break this down. Let's digest it. Hexane means we have 6 carbons, right? So we have 6 carbons. 1, 2, 3, 4, 5, and 6. 2 and 3. Well, yeah, that's not really good, is it? It's not really good, but let's try to just do it anyway. So 2 and 3 means that there's something on the 2nd and 3rd carbon. So there's something here and here. And let's see. Dimethyl means that there are 2 methyl groups. So we have a methyl right here and a methyl right there as well. Okay? And then we have a 3 chloro. So this chlorine group is going to be on the 3rd carbon as well. Let's do that right here. Right? And then we have a 5 bromo, so 4, 5, that's a bromo. So yeah, I mean, it's technically the same thing. Maybe it's a little uglier, but it's like the direct translation. So we have 6 carbons, 2 methyl groups, one of which is on the 2nd, the other is on the 3rd carbon. We have a 3 chlorine, a chlorine on the 3rd carbon, and then a bromine on the 5th carbon. So, you know, maybe just when you read your answer choice, you can write out the structure, right? The reason why C is correct is because we have a 5 bromo, and the reason why D is incorrect is because it has a 2 bromo. And I'd rather have a 4 methyl and a 4 chlorine. I'm sorry, I'd rather have a 3 chlorine and a 3 methyl compared to a 4 methyl and a 4 chlorine, because overall this methyl group is going to be 2, and I don't want a 5 methyl. I want to keep everything on the lowest number. The majority has to be on the lowest number. We cannot sacrifice a lower number for just bromine. It's not that special. You don't really care about it that much. You know, it's not imperative that it has the lowest number. So the majority of the substituents should have a lower number. All right, for this one, notice that we have an alcohol. Alcohol is super important to the economy, to people, to chemists, to everybody's life. Alcohol is really important. It's more important than double bonds, triple bonds, single bonds, halides, anything really in this basic chapter. So since it's so important, we're going to start naming, we're going to start numbering from the alcohol. So that's 1, 2, 3, 4, 5, 6, and 7. If you can't see that, here's kind of like a carbon base right here. Right. And we have a fluorine. Right. Okay, so the longest carbon chain will be 1, 2, 3, 4, 5, 6, 7. That's what? Heptane. Okay, since it's heptane, we can ignore answer choice A, B, and C because they have hexane. Hexane is 6, right? Like a hexagon. Heptane is 7. That's what we're dealing with. But since we have an alcohol, that heptane is going to get rid of that this E, right? We're going to get rid of the E and instead have an O, an OL, heptanol, right? Okay. And where is this location for the heptanol? Well, you can say that the alcohol is going to be on what? The first carbon. So we can say that this is a 1-heptanol. Now notice that answer choice E is incorrect because, answer choice D is incorrect because it says 7-heptanol. And they're numbering from 1, 2, 3, 4, 5, 2, 3, 4, 5, 6, and 7. They're numbering from the end. They're not numbering from the alcohol. Don't do that on the exam. Instead, number from the alcohol. Always, okay? Always do that. And so it would be a 1-heptanol. Okay. So that's the correct answer, right? Answer choice E. But let's continue this. We have a 3-fluoro, right? Okay. We have a 3-fluoro. We also have a 5-methyl, right? Methyl. And then we have a, what do we have? We have a 1-ol. Right? That's the prefix, that's the suffix for alcohol. It's just OL. So we can write this out. First of all, we have a 3-fluoro. We have an F right there. So that comes alphabetically. We have a what? We have a 3-fluoro, 5-methyl. 3-fluoro, 5-methyl. And don't forget your dash. 5-methyl. 1-heptanol. Okay? And another way that it could be on the exam is a 3-fluoro, so that's the same, 5-methyl. But then we're going to smush together the methyl and the heptanol. So we're going to say 5-methyl heptan 1-ol. So all I did was I took this 1 and I kind of like squashed it between the heptan and the ol. Right? So these are both completely valid answers, right? 3-fluoro, 5-methyl heptanol. If we want to actually analyze our answer, this means that we have a heptan. That means it's a 7-carbon molecule. We have an ol. That means that we have an alcohol. Where is this alcohol? Where is it located? Well, it's located on the first carbon. Okay? We have a methyl, and that methyl group is located on the 5th carbon. And then we have a fluorine, and that fluorine is located on the 3rd carbon. Alright, so the first thing that should pop out to you is that we have an alcohol right there. That's the OH group. Now let's do like a carbon skeleton. Right. Oops, sorry. Right there. Okay. We have this carbon attached to another carbon. Okay. So what do we have here? Well, I mean, we're going to start numbering from the alcohol, always. We're always going to start numbering from the carbon attached to the OH group, the alcohol. So we will say that this is 1, 2, 3. Okay. Notice that I went to the left. If I went to the right, we would have 2, 3, and 4. And you know, I'd rather have a 3 than a 4, right? I'd rather have a 3 than a 4. So 5, that's pentane. But notice that it forms a shape. That's cyclopentane. Cyclo just means that we're connected together in some sort of weird shape, right? Okay. And then we're going to number this. We're going to say 1, 2, 3, and 4. So that's a butyl. But notice something. This butyl group is attached to the cyclopentane via the second carbon. It's connected to the parent chain by the second carbon. And, well, that means that we have a sec-butyl. Sec-butyl. Cool. Right. And, you know, it's connected to the parent chain via the third carbon. So we will say that this is a 3-sec-butyl. All right. 3-sec-butyl. And this is what? Sec-butyl 1 cyclo pentanol. Alright, so let's read this. We have a pentanol. Well, pentan means 5, and cyclo means a shape. So we have a pentagram, or a pentagon, and the ol means that we have an alcohol. So where does this alcohol occur? This alcohol occurs at the first carbon. And then we have a butyl. And more specifically, we have a sec-butyl. A sec-butyl is just a butyl group that's connected to a parent chain via the second carbon, right? But this sec-butyl is connected via the third carbon for our parent molecule. So it's connected to this third carbon. Okay, another way that you can write this is you can say that 3-sec-butyl, we're going to squash these words together. Pentan 1 ol, right? So I ran out of room, sorry. So again, we just took this 1 and we kind of like squashed it between the n and the ol. So pentan 1 ol. That's another proper way to say it. Practice both methods. The reason why A is incorrect is because it has 1 hydroxyl. Yes, this is a hydroxyl group, but in nomenclature, you don't say hydroxyl, you say alcohol. And notice that it says cyclopentane. It doesn't say cyclopentanol. So that is incorrect. A is incorrect. Right? For answer choice C, it says 1 sec-butyl 3-cyclopentanol. Well, first of all, I don't see how you can start numbering from 1, 2, and 3. I don't see how you can do that. Alcohol is very important, so you start numbering from the alcohol. So answer choice C is incorrect. Let's see here. 4 sec-butyl. Again, they numbered going 2, 3, and 4. You know, I'd rather have a 3 sec-butyl than a 4 sec-butyl. Always keep your substituents on the lowest number. So 3 is lower than 4. Therefore, it's more favorable for us to have a 3 sec-butyl. Right? So that is just incorrect numbering. Right? And then we have a 3 isobutyl. Now that's not an isobutyl. I've never seen a molecule like that. Right? 3 isobutyl. Actually, isobutyl looks like this. Right? So it's like a Y shape. So that's 1, 2, 3. And then we have like the parent chain. The squiggly line just represents this. I'm lazy. I don't want to draw the pentagon. So this would have a 1, 2, 3, and 4. So that is a 3 isobutyl. Iso just means that it's a Y shape, which you see there, it's a Y shape. And then we just count the carbons, 1, 2, 3, and 4, so that's an isobutyl. We do not have an isobutyl in this molecule. So yeah, that was actually very informative. So if you catch anything, alcohol is very important. That's an isobutyl. This is a sec-butyl because it is attached to the parent chain via the second carbon, right? So we're asked to find bicyclo 322 nonane. Well, you know, if you've never seen this kind of nomenclature before, you'd probably be very worried. But this problem is super easy because we're going to be focusing on this bracket. So here's a little study tip to do, right? So instead, you got to focus on kind of like the carbons itself, right? So we're going to have brackets. We will say 1, 2, and 3. So that's 3. So what I'm doing is, notice that we have some bridgeheads. Well, first of all, let's actually finish this section up. Sorry. And this has 1, 2, 3, and 4. So that's 4, sorry. So instead, we will say that this is a what? This is going to be, sorry. That is a what? 4 period 3 0. Well, how did I get that? I'll explain it to you. Also, this is not the right answer. That's 430. This is 322. So this cannot be right. Let's say that this is 1, 3, 2, 4, and 5. Okay. So what I did here, let me just rewrite this. And let's kind of like break this right here. Do that. Okay. So right here, these 2 carbons are called bridgeheads. This is called a bridgehead. And this right here is a bridge that they're forming. Whenever you're naming a molecule that has a well, bicyclo means that there are 2 rings and they're fused together. What we do is we start numbering from the longest chain, and in this case, this I'm missing a carbon here. I'm missing a carbon. So let's see, there. So this would actually have a carbon right there. So I'm going to start numbering from the longest carbon. I'm going to say this is a 1, 2, 3, 4, 5. Actually, we start numbering from the bridgehead. 1, 2, 3, 4, 5, and 6. And then from the second bridgehead, we start numbering from the smallest chain. So that's 7, 8, and 9. Yes, this is nonane, but then we have to go into our bracket. So our bracket, we're going to start counting these carbons that you see here and here. Actually, here, right? So anything that is not a bridge carbon, we're going to count. And we have to do it in decreasing order. Okay? So I'm going to say that this is 1, 2, 3, 4. That's 4, period. Not comma, it's a period. Then we go to the other chain. Well, that's 3, right? And 3 is less than 4, so we'll say 3. And period. How many carbons are in this line? Do you see a carbon like this between these 2 bridgeheads? No. There are 0 carbons in here. So that is a 0. That is 430. Nonane. So it's bicyclical or bicyclo 430 nonane, and that is not what we're looking for. Right? So that's kind of like the basics for naming bicyclical compounds. So with that in mind, let's do another one, and let's actually write out the carbons as well, so you can see it. Let's do problem 3 as an example. That's a carbon, another one, Oop, that's kind of looks like an oxygen. And then let's do it like this. Okay, so that looks like a mess, but when you connect the dots, it looks pretty good. Right. So those two carbons are kind of like facing upwards. They're facing out towards you, right? And I like to look at it as kind of like a swimming pool that has water. So you walk over here. Oop. You walk over here. This is like a swimming pool, and this is kind of like the diving board. You climb the ladder, and then you cross a bridge to the other side, or you can like do like a diving board type of thing, right? And so it doesn't matter that they have like 1, 2, 3, 4, 5, 6, 7, 8, 9. It doesn't matter if it has 9 carbons, right? We're gonna count the bracket first. So which one is gonna have the most carbons? Well, let's count from the center carbon. 1, 2, 3, and 4, 5, 6, 7. Now we're back at this center carbon. We're gonna go up the ladder, say that this is 8, and that's 9. Okay, so we have 1, 2, 3 carbons on one side. On the other side, we only have 2 carbons right here. So that's 2. That is 2. And then for this one, we have 1 and 2. So there are 2 carbons right there. And hey, look, it's exactly the same thing. We have 3, period, 2, period, 2, period, nonane. There are 9 carbons in decreasing order, that is 3, 2, 2. So hey, number 3 is correct. For this one, we're not going to draw it out because it takes a lot of time. That is what? We have 1, 2, 3. Okay, we have 1, 2. So we'll say that's 3. That's 1, 2. Period. This is 1 carbon. So that's 3, 2, 1. That's not what we're looking for. Bad. Okay. On the other side, we have 1, 2, 3. 1, 2, 3. So that's 3, 3. And then we have 1 carbon in the middle. That's 1. Not what we're looking for. Bad. Right here, we have 1, 2, 3, 4. 1, 2, 0. So 420 is not what we want, okay? And so this is incorrect. So just by doing the simple bracket trick, you can eliminate all of them. You can eliminate all the answer choices except for number 3. So I hope that this helps you in naming bicyclical compounds. For this question, we are going to use a strategy of just naming the compound. Well, not naming, but numbering. When you have a double bond and everything else is like a halide or a simple alkane, right, you're going to start numbering from that double bond. So we start numbering from here, 2, 3, 4, 5, 6. Am I going to say 7? Well, I mean, you could. Let's see, 1, 2, 3, 4, 5, 6, 7. And, wait, hold on. Yeah, so this is actually 7 and 8. Now you're probably wondering, hey, isn't that like a isopropyl? And you know, technically it is. Technically it is an isopropyl. But look at your answer choices. Right, look at your answer choices. For B, D, and E, you have heptane, heptane, and hexene. Well, this is definitely more than 6. So even if you were to number like here, 7, well, that's more than hexene. So answer choice E is incorrect. And then heptene, well, frankly, I mean, it comes with practice, really. Like, this is not an isopropyl in this case. It's just a 7 and 8, right? So it's kind of being a little flamboyant, a little bit ostentatious. Just say that it's 7 and 8. And if you do that, 7 and 8, then you eliminate answer choice B and D. So you only have A and C. I know it's not the best explanation, but it works for me. So this is a 4-bromo. 4-bromo, This is a 3-methyl, right? And we have a 7-methyl. Now, where does the double bond occur? Well, it occurs at the first carbon. We don't say that it occurs at the second carbon because between the two carbons that it occurs in, 1 and 2, we'd rather name it, we'd rather put the location on the smallest carbon. So 1 is smaller than 2, right? So we say that this is a 1 double bond. Or you could say that this is a 1-ene, right? So that's a 1-ene. So let's put this all together. We have a 4-bromo alphabetically. 2 methyls means that it's a dimethyl, and hence we will say that this is, oh, sorry, I have a methyl right here. So that is a 6-methyl. That means 3 methyls means that it's a trimethyl, and they occur at 3, 7, 6, trimethyl. And what do we have here? Well, we have a 1-heptene. Oh, I'm sorry, not a heptene, but a octene. Octene. So this means that we have 8 carbons in our molecule. There's a double bond because of this ene. It occurs at the first carbon. We have 3 methyls, which occur at 3, 7, and 6. And actually, it shouldn't be 3, 7, and 6. It should be 3, 6, 7. So number in numerical order. And then we have a bromine, which occurs at carbon 4. And that corresponds to answer choice C. The reason why A is not correct is because you put the bromine after the methyl. And, you know, M does not come before B, right? That's not right. So it's alphabetical. We should have a bromine first because of the B, and methyl because of the M goes afterwards. So yeah, this, I mean, I would say that it's an isopropyl, but in this case it's not. Just go for like the vanilla, you know, longest chain trick for this type of problem. So for this question, which is number 11 on your practice exam, I'm not going to draw it out because it's a lot. However, I will draw out the correct answer. So you would have a circle, right? And Newman projections work like this. This peace sign that I drew out, it means that there is something pointing towards you. It's coming out towards you. In this case, right here on the one of the tips, we have a hydrogen, a CH3, and an H. Okay. Now on the other one, we have some things coming out in the back, and actually kind of looks like this. Looks like this. Sorry. So this is referred to as eclipsed. So the 3 lines that I just drew are in the back. So there's something in the back. And on the next example, I'll show you a really good example of a Newman projection. But essentially, you're just holding up a molecule and looking down the barrel. You're looking down this carbon, and there's something behind that carbon which takes form as these 3 lines. These are not methyl groups, these are actually the bonds. And so that would be a hydrogen attached to that one, a CH3, and another hydrogen. This would be really bad because notice that these methyl groups, the CH3 and another CH3, are really close together, and they experience something called steric strain. So steric strain is, for example, let's say you're trying to get on a bus, and these 2 sumo wrestlers come in the bus, and they try to sit next to each other, right? And those seats are pretty small. So 2 sumo wrestlers are going to experience steric strain, right? Steric, and the S can be also sumo, right? And so those sumo wrestlers are going to kind of like push and shove against each other, and they're not going to be happy. They're going to be bumping a lot. So it's when 2 big molecules collide. They hit each other, And whenever they hit each other, the electrons also hit each other. And when electrons bump into one another, well, that's not good because electron is negative and electron is negative as well. So it's like getting two magnets and trying to put the same pole together. They're going to repel. Whenever electrons repel, that's called a torsional strain. So, yeah, this is really bad. Torsional strain is for electrons only. They're going to be bumping into each other and they're going to repel. They're not happy. Steric strain occurs when two molecules that are big are really, really, really close to each other and they bump into each other and they push and they shove. That's not good. This molecule has, let's see here, it has kind of like, it has both steric and torsional. Steric because these two molecules are big and they're going to be bumping into each other. And torsional because their electrons are going to be bumping into each other as well, and those electrons generate torsional strain. The more strain you have on a Newman projection, the more energy it takes to kind of like rotate, to kind of do anything with it. So the more strain you have, the more energy, and you don't want that. You want to have the lowest energy. You want to be calm. You want to have the most stable projection. And so this format right here, where everything's really close to each other, that's called a total eclipsed. Total eclipsed. Notice that these hydrogens, they're not steric strain. Yes, these two are very, very close to each other, but they're so small that they don't really touch. However, they experience torsional strain because their electrons, their electrons collide and they try to repel each other. So they have torsional strain. However, they do not have steric strain. So because this molecule has both steric and torsional strain, it's going to be the least stable conformation for butane. So it would be answer choice B. So for this problem number, I think it's question 12. We have a molecule, and we're asked to look down this carbon, the second carbon and the third carbon. So what we're looking at is that we're looking at carbon 2 and carbon 3. Okay, so we're looking at carbon 2 and carbon 3. And we're going to be looking down the barrel, looking down directly on the carbon right there. You see? You see how nice that is? Well, when we're looking down the carbon, we have to actually realize that over here there is there's actually a double bond, okay? And I can't rotate it in this program, but you would be able to rotate it on your model kit via the single bond right there, not here. So you can actually rotate it towards the right or towards the left. So let's imagine that this double bond is right here and that you can see it. Okay, so this allows us to see that that this is, oh, sorry. So right here, we're going to have a CH3. Okay, we have a CH3 right there. So that's a carbon with 3 hydrogens. We can also see this oxygen, this alcohol right here. You see this alcohol? We can see that. And also, if I were to rotate it, this right here would be viewable. Sorry, this would be viewable right here. So we can see the CH3, we can see the alcohol, and we can see the carbon. However, we cannot see this carbon right there. Right? Oh, and we can see this double bond as well. Okay, so what are our answer choices? Well, for number 1, we have a CH3 bond on top, but notice that we don't have an alcohol, so they're completely ignoring alcohol right there, and so number 1 cannot be correct. Okay, well, what about number 3? Well, number 3, it's saying that we have our carbon double bond towards the bottom, so it's kind of like upside down, if you can imagine that, which is not good. let's see what else. I mean, it's a very difficult problem because it's not asking for like the most stable. It's just saying which one is illustrative. So yeah, you should expect two CH3 bonds right there, which we have, right? But why is 3 not correct? Why is it not correct? Well, let's see here. Well, it's not correct because I really wish I could rotate this. But if you were to have the rotation, let's see if I can do it without messing it up. So that's on the y-axis. It's on the x-axis. That works. So let's say that it's like this, right? Well, it turns out that the program froze. How nice. That this alcohol is towards the left-hand side. It's not on the right-hand side. It's a completely different molecule. Number 3 is saying that we have a CH3, which is correct, and then an alcohol right here. That's not true. We have an alcohol towards the right. Okay? It's towards the right. Or the left, sorry. So number 3 is incorrect. Okay? It's incorrect. Number 4, yeah, we have an alcohol on the left and then a carbon, a CH3 on the top, and an alcohol, or sorry, a hydrogen on the bottom right. So why is it not correct? Well, let's see here. Let's see. We have a hydrogen, yeah, pointing this way. Then we have a CH3. Aha, see that? So right here would be your double bond, and right here would be your H. Now notice that on number 4, the H is kind of like over here, right? And then the so the H, which is where you see the white ball right here, it would be here, and then the CH3 would be over here, right? And this double bond would be in the place of CH3, which is not correct. So basically, they got this number 1 and number 2, they swapped places, and that's a completely different molecule. This would be incorrect. So number 4 is incorrect because this would have to be a double bond, and that would just have to be a CH3. And that's not what we have. We have a double bond on the right-hand side, and we have a CH3 on the left-hand side. Number 4 is saying the opposite, so that's not correct. So we only have 2 and 5, which is the correct answer for 2 and 5. For 2 and 5, if the program weren't freezing, it's my luck, right? We can actually rotate it and have the double bond on the top. And if we have the double bond on the top, then this right here would be kind of like rotating downwards, right? It would rotate downwards. And if this rotates downwards, then the alcohol rotates upwards and it hits the left-hand side, which is correct. That means that this hydrogen would be like up here as well, if you can see that, kind of. Yeah. So that would be correct. And number 5 is also correct. This is just a double bond on the bottom side. The alcohol would be on the right side. If the alcohol is on the right side, then this would have to be what? The CH3 would have to be here. And the hydrogen would have to be up there, right? It's kind of like, if you can see it, right? I wish that it wasn't frozen, but then those are the breaks, right? So for number 13, we are dealing with the most stable conformation. So what is the most stable conformation for 2,3-dibromobutane? Well, I can straight up tell you that number 2 is incorrect because that is total eclipse. That's the worst one. It has both torsional and steric strain. So that's not good. And instead of drawing the Newman projections, I'm pretty lazy, so I'm just going to draw the molecules out. CH3, H, H, and I'll come back to you when I'm done. Alright, so it's really asking which one is going to be the most stable. Well, kind of use my sumo example. Do I want 2 sumo wrestlers sitting on the same side of the bus, right next to each other? No, because this generates a lot of steric strain. Steric has an S, like sumo wrestler. And so this one would not be correct. This is bad, because we have 2 bromine atoms, which are really huge, sitting right next to each other, and they're going to be bumping. That's not good. we have a bromine right here and a bromine right there. They're far apart from each other. This is another sumo wrestler, that's a methyl, and another one, another methyl, and they're sitting across from each other. So they're not bumping into each other, they're happy, they're sitting very well with each other, right? So since they're not bumping into each other, they're going to be very stable. So this gives me kind of like a happy face, right? Okay. Over here, yes, we have a sumo wrestler sitting across from the other sumo wrestler, but then again we have two right here, and they're sitting right next to each other. So that's really bad, right? They're taking a lot of room. And the same thing is happening here. This is not good. That's bad. They experience both torsional and steric strain. Not good. This is not favorable. However, we do want configuration 3. So answer choice 3 would be good because they're sitting far apart from each other. This is okay, right? Technically, the bromine is a bit bigger, if I recall correctly. It's a bit bigger, and this one is a little smaller than bromine. So it's okay that they're close to each other. We just don't want two of the same things sitting next to each other, because that's really bad. So again, which one is going to be the most stable conformation for 3-bromo-2-methylpentane? Well, if you notice on the first formation, you're missing this structure. And so by deduction, you could say that this is bad. It's not even the same molecule, right? And over here, I actually don't know what this is, right? Like, what is that? That's also not good. So we can take that off. Okay. And over here, you notice that we have 3 sumo wrestlers of the same variety. This one's huge compared to the other 2, and they're sitting right next to each other. And that's not good. That's not good either. Yeah, we have a bromine sitting right next to a methyl, but bromine's a lot bigger than methyl, so it's not too bad, right? They're not the same size. And this one, I mean, this is not favorable, right? But, you know, it's better than the other ones. And the difference here is that the hydrogen was over here, but now it's kind of like sitting between the methyl and another methyl. So it kind of alleviates some of the strain. So this would be like a pretty good formation. Number 2, which I didn't write here, is completely total eclipsed. So it's going to have a lot of steric strain. It's going to have a lot of torsional strain. It's not going to be favored. Too many sumo wrestlers are sitting close to each other. You don't want that. You want to have them at an angle where they're not completely eclipsing each other, if that makes sense. Okay, so now it's asking, what is the preferred conformation for cis 3-tert-butyl 1-methylcyclohexane? Wow, you know, oh my gosh, organic chemistry is so hard. This question is not too bad. It's asking us for something that has cis and it's methylcyclohexane. So now I'm going to introduce to you the concept of chair conformations. So to do a chair conformation, it's going to be like this. It's kind of like a peak right here, like that, up, downwards. And if you want to do like a left-hand variant, which I'm not really good at, it's going to be like this, boom. So what am I doing? Well, let's try to do this in 3D. Let's see if I can help you. Okay, so I'm hiding the hydrogens, right? So I'm hiding the hydrogens, and right here we're dealing with a hexane. Notice that this is a 1, 2, 3, 4, 5, 6 hexane, right? So it's a 6 hexane. And what you're doing is you're seeing me kind of like move this molecule to have kind of like a bent shape. So you see that? It's like a Z. And you can actually sit here. This is why it's called a chair conformation. So it's kind of like a seat, and all you're doing is that you're making that hexane lie on the ground at an angle. That's all we're doing. And so you'll see me kind of like drawing these structures, and that's called a chair conformation, right? And so the left-hand structure is going to look kind of like this one, so it's going to be downwards. If I can actually move it, that'd be nice, but I can't. So that's kind of like a left hand, and this is going to be like a right hand, right? Downwards. So I hope that helps for you to see what I'm doing, right? So that's just a chair conformation. It's like a 3D model. We're going to have kind of like axial means axial, it goes upwards. And then equatorial means that it's going to be kind of like straight. So it's kind of like the equator. And right here is going to be axial. If we put something, it's going to go straight up. And then equatorial is going to go straight out. Not downwards, but straight out. Alright, so I hope that helps you see what I'm doing in this model, right? I hope it helps you. So when it says cis, all it's asking for is for the substituents to be on the same direction. But what kind of direction are we going to be dealing with? Well, you're going to be dealing with up and down. So right here, let's do it in a different color. This would be upwards. And yeah, that would be upwards. And then this would be downwards. So up, and this is down. Also, this is axial. And this is going to be equatorial. Right? Because it's kind of like on just like straight out. It's not going upwards. It's just equatorial. Okay. Now, it's important for you to know that the most stable chair conformations are going to be equatorial, not axial. So I'd rather have my substituents on the equatorial. And when it says cis, it means that both of my substituents are going to be equatorial. Trans means that one of them is going to be axial and the other one's going to be equatorial. So let's start here. We number our carbons like this: 1, 2, 3, 4, 5, and 6. Okay, so that's 6. So we have a methyl on the first carbon. And whenever you do this type of problem, just kind of like do your axial and then your equatorial. And we're not going to write out, another methyl, because that's confusing sometimes. So we're just going to substitute it as Me. Notice that I put it on my equatorial first, because that's the most stable. I'm not going to put it on axial. That's not good, right? So I'm going to put it on equatorial first. And we're going to put a hydrogen right here. Okay, so 1, 2, 3, 3 right here. So we have equatorial, we have axial and then equatorial. You see that? It's kind of like a cube. So equatorial can make a cube shape. Okay, so axial goes up or down, equatorial goes straight out on the horizontal. And hey, this is cis. So we're going to have to do what? We're going to have to do equatorial as well. So instead of saying T-butyl, instead of writing out a tert-butyl, we're just going to say T-butyl. That's a bad B. And this is what? This is going to be yet another hydrogen. Okay, so that would be the most stable conformation for a chair. And notice that both of my groups are going to be equatorial. So it's going to be answer choice D. Right? I don't want to have something that is what? That is axial and the other one that is equatorial. Because if one was axial and the other is equatorial, that's trans. They're both on equatorial. So that is cis. Cis means the same direction. Trans means to be in different directions. Right? So, yeah, this would be the most stable conformation. I hope that helps your perspective, the 3D model, So we have to name this molecule. Notice that the chlorine is coming at you over here. That means it's facing you. However, on the other side, it's in a different direction. It's going towards the screen. It's going into the white paper. So that means, because they are not in the same direction, they're not facing you. One of them is facing you, the other one is facing towards the paper. This is going to be a trans. So we can automatically eliminate answer choice A and C. And we can eliminate answer choice E because it does not have cis or trans. It just says dichlorocyclopentane. Okay, well, you can say, as you number it, you can do 1, 2, and 3. I don't want to have 2, 3, and 4 because then this chlorine would be on carbon 4. I'd rather have it on carbon 3. Okay, so this is a cis 1, 3, dichloro, cyclopentane, which corresponds to answer choice D. It's trans. So now we're asked to find trans 1,2-dibromocyclohexane. Which one is it going to be? Is it going to be 1, 2, or 3, or is it a combination? Well, if it's trans, one of them has to be upwards and the other one has to be downwards. Let's see the problem here. This one is was equatorial, right? It's equatorial, and this one is axial. However, this one is directing upwards, and this one is also directing upwards. This is down. Let's call it a D. And this is also down. Notice that these are both upwards. That's not good. That's cis. So relative to that carbon, bromine is going to be upwards, and relative to this carbon is going to be upwards. Now, in this carbon right here, hydrogen is upwards, and bromine is downwards. Right? So, I mean, bromine would be at an angle, so it's directed downwards. Now, this one is kind of upwards relative to this carbon, so it's going to be up. This is going to be down. So, down, up. Hey, that looks pretty good. That gets a check mark. They're in opposite directions. Well, this one is up, and this one is down. So, hey, that's pretty good too. So 2 and 3 are good. That's your answer. Answer choice D. So, yeah, it's just up or downer mentality. This one is going downwards, this one is going upwards. This one is going upwards, the other one is going downwards. Alright, so let's draw this molecule. Well, it's trans. If you see a trans and then you see like a cyclohexane and a lot of mess, well, you're going to have to do the chair conformation. I like doing the right hand chair. Right? Okay. So, yeah. Right here, we start numbering, so that's 1, 2, 3, 4. So I'm going to do this right here. Oh, sorry. So yeah, this is how you draw it. I mean, it's good practice anyways, drawing it. So let's see here. We have, I like doing axial first and then equatorial. So that's 1, 2, 3, 4, and then axial up here, equatorial. Since they let me kind of write it out, I always want to start with my equatorial first. So this is the first carbon. We're going to put a bromine on the equatorial, period. That's it. Then that's a hydrogen. Now, normally I want my other one to be what? I want it to be on the equatorial as well. But notice that this is kind of like, I mean, yeah, this actually is a hard one. It is a hard one because normally I would draw it like this. I would draw it with methyl and then a hydrogen, right? But notice something. Notice something. These hydrogens are going to be away from each other. They're going to be away. I mean, well, not away. They're going to be invisible, right? And notice that this is indeed a trans. It's trans. It's not the best one though. Because really, I messed up. You should have been like, to make it more obvious, you could put like a, put like a H right here. You could put it up or down. Since you wanted trans, I was supposed to put it down and the other one up, right? So yeah, this is kind of like upwards, and this is going to be directed downwards. So this is down, and this is going to be up. So yeah. The bromine is upwards and then the methyl is downwards. They are trans. They are in different directions. Bromine is up, methyl is down. That is trans. If I wanted cis, cis is not going to be as stable because we're going to have the methyl on the axial position, and that decreases stability, so the trans would be a better option. The cis, however, would be terrible. We do not want to have up and up because this would be on the equatorial, which is good, but the methyl would have to be on the axial, which is terrible. Always avoid that. So yeah, my apologies. You can have the H going up or down, In this case, it's better to draw it downwards because it makes the answer choice more obvious. So answer choice A would be correct. Notice that answer choice B, it has the bromine going downwards and the methyl group going downwards. That's incorrect. That would be cis. For 3, what do you have here? Well, you're supposed to have the methyl group on the 4th carbon. However, the methyl group on number 3 is on the 3rd carbon, so that's incorrect. Right? That's incorrect. On number 4, you have the bromine on the 2nd carbon, which is not correct. You want it on the 1st one. And then for number 5, this is correct placement, but they're both cis, so they're both pointing upwards. You want one pointing upwards and the other one pointing downwards. That makes it trans. So which one of these molecules is cis? So cis means that they're in the same direction, meaning that they're both up or they're both downwards. Notice that this alcohol is going upwards and this bromine is going downwards. So this is trans. Nope. Right here, chlorine is going downwards and methyl, CH3, is going downwards, and that's cis. Okay, we have a fluorine going downwards and a bromine going upwards. This is trans, not good. Right here we have an alcohol going downwards and then a methyl going upwards. This is trans. We don't want that for this question. Then we have, I believe that is a ethene or ethyl group, and it is going upwards, and then we have a methyl group going upwards as well. However, this is not stable because they're both on the axial position. I'd rather have them on the equatorial position, but that question is not being asked. However, we're being asked for cis, so this is cis. They're both going upwards, or they're both going downwards, you see? So it would be answer choice B, 2 and 5. Okay, so we're asked to find an alkene that would give us a 3-methylpentane when it's subjected to catalytic hydrogenation, hydrogenation. Well, first of all, this is what we want, right? This is what we want. And if you don't know what catalytic hydrogenation is, like I do, I don't know it, but this is actually, you can eliminate a lot of the answer choices. Okay, so we want a 3-methyl, right? This is a 3-methyl right here, and this is a pentane. Well, answer choice A, C, and E are incorrect, and also D. So A doesn't have this methane, this A does not have a methyl. C does not have a methyl. D has a methyl, however, it's on the 2nd carbon. We don't want that, we want it on the 3rd carbon, so that's incorrect. And then E also has it on the 2nd carbon over here, so that's incorrect. So the only one that could be possible is B. So you can say that catalytic hydrogenization, or whatever, hydrogenation, is just a removal of a double bond. You can say that. So when you remove that double bond, you get a 3-methylpentane, which is what we want. So if you know how to draw a structure, then you would know that you need a methyl group on the 3rd carbon. The only one that gives us a methyl group on the 3rd carbon is answer choice B. I hope this video helps you. I hope you do amazing on your exam. Of course, you got to do a lot of practice problems for nomenclature, and I recommend that you do chair conformations with your structural molecule sets. Those are really fun, and I have a lot of fun doing this. I'm glad that I can help you, and I'm glad that you find these videos helpful. So please have a great day, and thank you for watching.